Our next presenter is Josh Revels. He will be presenting the James Webb Telescope. He's an education specialist at the NASA Independent Verification and Validation Education Resource Center in Fairmont, West Virginia. He is a graduate of Fairmont State University in Fairmont, West Virginia, and currently has a master's degree in education with teaching certifications in chemistry, earth and space science, physics, and general science education. His main goal at the Katherine Johnson NASA IV&D ERC is to train educators to implement activities relating to content involved with NASA missions. Like most, he has loved astronomy since he was old enough to look up at the stars. Just looking into the vast beauty of space sparked his curiosity and admiration for the universe. With his Dobson telescope, he enjoys showing teachers and students how to hunt for planets as well as locate nearby messier objects. His first being the Great Globular Cluster of Hercules, or M13. This was his first celestial object he ever created an image with, and did that by using the Yerkes 41 telescope. Now he is looking to finalize his planet hunting checklist. So far he has observed Mercury, Venus, Mars, Jupiter, and Saturn.
Mercury was during a training. What's your name? Would you like to help me with something, Mackenzie?
Yes, she would.
Okay. All right, Mackenzie, we're gonna start by demonstrating something. Let me set up my PowerPoint. I'm gonna step back over here, and I'm gonna point my camera at you. Okay, you see yourself? Wave at the camera for me. Okay. Cool. Bigger wave than that. Nice big wave. Swing your arm around so everyone can see.
Like this.
Really high, like over your head. Way over your head. There we go. Okay. Wow, look how warm your hand is. So the white colors in here are objects that are hotter. And as you can see, maybe you can see the scale here. If not, come up later after the presentation and play around with this. The purple and the darker colors are cooler. And that's because heat gives off infrared energy. So I'm using a FLIR camera here, and we are seeing the infrared energy that's out in the room. And it's much cooler now than it was earlier. It was really bright yellow and green whenever tonight started. Okay, I'm going to have you, Mackenzie, wave one more time at the camera for me. And I want you to do it with your hand inside of this NASA bag. It's an opaque bag, meaning we can't see through it visually with our eyes. Let's see what happens. Okay, nice big wave again. So you can still see Mackenzie's hand in the bag using this technology. All right, so don't go anywhere yet, Mackenzie. You should hold this in front of your face for me. Okay, ready? Where'd she go? She's gone. So this transparent material in infrared has been blocked. It's not allowing that infrared energy to transport through that material to be seen here. This is pretty interesting, right? All right, so I'm going to leave this here for everyone to try out. Thank you, Mackenzie. Everybody give a round of applause. So, do you want the lights on or off? No, this is fine. Okay. And I downloaded my presentation as a PDF. So I can't, I'm not sure I can make it any wider than that. Yeah, so tonight I want to talk about the James Webb Space Telescope. I'm going to give you a little bit of an update. We're going to take a look at some of the images that were captured using the telescope, or that were created using data from the telescope. So, anybody been keeping up with this? Okay, cool. So, so the big difference here between our telescopes is one of them is an optical telescope, the other is an infrared telescope, like the technology that I was using here. The Webb Space Telescope, which is the one on the left, has the infrared capabilities. And the Hubble Space Telescope is the optical. And so back when I was born in 1990, this thing launched and went to space. And so here we are, 32 years later, looking at images from this telescope. And so Webb is just furthering the exploration of the work that Hubble has done. And so when I talk about infrared radiation, I'm talking about the properties of the light that make it classified as infrared. And so that is the wavelength, the frequency, and the amount of energy that the light has. And so this is all the different types of light that we know about. So we go back to asking about what dark matter is. There's probably also energy out there that we are not really sure of as well. And so you can notice here that on the left we have really big waves, and then we work over to the right, and the waves get crunched up and smaller and smaller. So these waves on the left have high wavelength, waves on the right have low wavelength. But opposite of that is their frequency. If a wave has a big wavelength, its wave is not as frequent, right? There's less waves that can pass through. But if I have a small wave, that means that the number of waves that pass through at a time is greater. So the frequency is larger. All right, what do you guys think? Anybody know which one of these has the most energy? Yeah, Matthew, which one do you think?
The gamma ray.
Yeah, these waves that have high frequencies have more energy because there's more waves hitting at once. And so John was talking earlier about eyes. In the back of our eyes, on our retina, there are photoreceptors called cones and rods that can detect energy only within the 400 to 800 nanometer wavelength. That's this section right here. And so we can see red, green, and blue colors because of those different types of cones in our eyes. And so that sends a signal to our brain and helps us see what we see. And so infrared is not something that we can see naturally with our eyes. We use this technology to create a false color image of what it might look like instead. And so, as you saw, some of these materials are better at absorbing infrared than others, and some of them just let it pass straight through. This is a list of very common chemical bonds between atoms that absorb infrared energy. At the very top here is the carbon-hydrogen bond found in alkanes, so like methane. We also have a hydroxyl group on here, the OH. This is a bond that's like in water. So these things are things that you're actually very familiar with. They're in our air, we breathe them all the time. And so these are very common bonds too in molecules that make up our atmosphere and the greenhouse gases in it. In fact, that's what makes our greenhouse gases. They absorb infrared energy and then they re-emit it in a different direction. And so that helps keep our planet warm. Anyway, as we learned, the atmosphere distorts our images, right? When we're looking out into space, it could become a problem. In fact, light pollution is a problem because of these particles that are in the atmosphere that the light's interacting with. And so we have to get away from this atmosphere to help us look clearer into space. And so we tried this from the ground with infrared, other infrared telescopes before, like these two here, Tech 1 and 2. These work because you have to go to a very dry climate and go to a very high elevation. They're like 14,000 feet elevation in Hawaii. And then we have the Sophia airplane that NASA did a lot of experiments with. And it has a telescope on it because it can fly up at a point above a large portion of these gases and get better observation. And then the Spitzer Space Telescope on the bottom was launched in 2003, and it trails behind the Earth, and it's an infrared telescope. All right, we're going to talk more about the recent infrared telescope, the James Webb Space Telescope. Take a look here at the objective lenses of these two telescopes. Notice how different in size they are. One is like the size of a high school, and the other is like the size of a schoolhouse, right? One is much bigger. That means that it has the ability to capture more light at once. And that light is what we need to actually observe what we see out in space. If you collect more of it, you're going to get better images. And so it has about 6.25 times more collecting area, and it makes it about 100 times more powerful than the Hubble Space Telescope. The telescope was named after NASA's second administrator, James Webb, and it is the largest telescope that's ever been put into space, and happens to work, which is great. So some other things that are interesting about it are that it has these hexagonal mirrors that are made of beryllium, and they have about 1,000 atoms of thickness of gold across them. And that's just to help with the infrared resolution that it is dealing with. And it's really big, right? It's about the size, the base of it is about the size of a tennis court, and it's about 3 stories tall. And it had to be folded up to fit into a rocket that was 5.5 meters wide. And so, because of that, it has a deployable sun shield. That's the layers of metal there that you're looking at. The mirrors actually fold up. The receiver that's out there folds up. It was folded up at one point in time as well. And so these things had to be designed to automatically unfold on their own. So the folks, the software engineers at NASA, IBM, and Fairmont, West Virginia, actually worked on revising some of the team's work and making sure that all of this unfolding, the sun shield, the meters, all of it worked perfectly. And so the fact that it did is really a testament of their hard work. So they were really happy and proud on Christmas morning whenever they watched this thing launch off back in 2021. Did anybody happen to catch that? Walked in on TV then? It was cool. I grew up in a time whenever everyone was talking about the Apollo missions and going to the moon, but I never witnessed it. And so that was, for me, this was like, whoa. Space exploration is a thing, and it's really awesome. And we're about to see that unfold again with the Artemis mission. So I just have this in here as a video that I did. We're going to skip past that. But it took about 30 days after launching to reach its orbit at the Lagrange 2 point, which is 1.5 million kilometers away from the Earth. You might be wondering what the Lagrange point is. Oh, notice where Hubble is orbiting the Earth. Webb actually is orbiting the Sun along with the Earth. And so Lagrange point is a point where in an orbit around massive objects where things seem to stay in place. So these are good places to put things that we're observing space with because we can keep control of them. And so you can see there the L2 point, and that's actually how the James Webb Space Telescope orbits. It moves like this around the Earth while it also orbits around the Sun. And you can see here how it's kind of tilted like this, and that's so that the sun shield can block the sun's light and keep all of the science instrumentation on it cool and working effectively. You can go on the web to Where's Webb,
and actually watch this data in real time, see what the temperature is of the different things that are there. Okay, this slide's a little outdated. They wanted to launch this thing in 2020, and it kept getting put on hold for various reasons. And so it did finally launch Christmas morning of 2021. And these are the goals and objectives that it has. It's going to detect the first light after the Big Bang, finding and studying the first luminous objects, protogalaxies, supernovae, and black holes. It's going to look at assemblies of galaxies, studying the merging of protogalaxies, the effects of black holes, and the history of star formation. It's going to look at the birth of stars and planetary systems and study how stars form in dust clouds. You saw some of the photos earlier of the pillars of creation. Those are regions where we think stars are forming inside of those clouds. But we can't see that happening if we use a visual telescope. That material blocks that. So using infrared allows us to peer into those things that are opaque to our eyes to see what's happening. And they're doing a lot of, recently they've been putting out a lot of images of planets, and they're learning about the atmospheric patterns on some of our gas giants, which has been really interesting to me too. There's another image of the pillars of creation. And this is, like you mentioned, it was made famous by the Hubble telescope, which launched in 1990. Something that I didn't learn until I was in college was that the telescope wasn't really that useful until 1993. They had to plan a mission to go and correct its vision. So they put this, I guess, like you could say, like a pair of glasses over its objective mirror so that it could work correctly. And then it cleared up the images. And so why did they even send Hubble out? Well, it was to get out of that atmosphere, like I mentioned earlier. The distortion of our atmosphere is something that affects how we observe things. So if we can get out there and closer to the objects, we can see them with better detail. And then Edwin Hubble. Oh. Based on the specs up there on this instrument. I don't talk about this instrument. I'm not a history teacher, but I know a bunch of people that are. Go right ahead. Edwin Hubble actually wanted to find some evidence to show that the universe was expanding. So these galaxies and things were all moving away from us at different rates. And he did that by measuring what's called the redshift of these galaxies. If he knew that they were moving away, because he could see that their light was shifting from one color or one frequency or wavelength to another, that would indicate it's moving away. I'm going to explain that further in a second. And so telescopes are, in a way, like time machines. When we look at things, we are looking back in time. I'm going to take a second here. Joe mentioned this earlier. But what's the light here? This is the distance that light can travel in a nanosecond, which is a billionth of a second. Okay, so imagine, I've got a good one for you. You all had some good ones, and this one's good too. So if you're looking for, you're out there and doing something in the field, doing some astronomy, you can always tell your loved one, well, honey, you always look younger to me than you actually are. And that's because you see her, right? Or you see them at the light that would be coming off of them. And here, it takes a nanosecond, right, for it to actually get to you. So that is true, actually. So how do we know if things are moving away from us? What's the redshift? What's that? So this model here kind of describes that. You all have heard and seen emergency vehicles and heard their sirens going, and you've probably seen one come closer to you and it passed by, and you've noticed the difference in the sound, right? At one point the frequency is getting higher as it approaches, and then as soon as it passes you, it starts decreasing. This is the Doppler shift. And the same thing works for light. If I were to move light closer to somebody, the waves are going to scrunch up. They're going to get smaller. So the frequency becomes greater. There's more energy, but it also, for visual light, it would change the color to the blue side of the spectrum. Redshift is the opposite. The waves start stretching out, the wavelength gets bigger, the frequency gets smaller, and so we call that redshift. And so Hubble was able to show that things are moving away from them. So for the James Webb Space Telescope, we're looking at infrared light. And that technically is red-shifted light that was once visible light. Right? It's moving to the red side. And so with the Webb Space Telescope, we can look further back in time with it. And because this is a PowerPoint, my animations aren't happening. So sorry that some of the images are cut out on here with my thing laying on top of it. But on the left is the Hubble Deep Field image. This is the first wide-angle photo of galaxies that we ever saw with the Hubble Space Telescope. On the right is a similar image taken with the Webb Space Telescope. So you could notice a few things in here. First thing that I noticed is recognize that this pattern, there's 8 little spikes coming off of these stars, right? Over here you don't see that. You see a different pattern. And this is because of the hexagonal mirrors on the Webb Space Telescope. They create that phenomenon. Also, you probably see that some of these galaxies and things look like they're warping or twisting, right? That's similar to why that magnifying glass in my image is doing that to the words I'm using. The mass of these other galaxies are bending the light coming from them and creating that effect. And there was one more thing, maybe you can't see it real well. So there are some stars up here. You should probably come up and look at my screen at some point to look at it. But there's what's called a diffraction pattern. It's like a rainbow of colors coming out from the star. This is another thing that's super cool and unique about these stars. And it's just because it's in the infrared, it's just making the stars appear brighter than they are. Okay, so Webb also has a mid-infrared range as well as a near-infrared range. So these are two of the same locations in space taken with those two different types of instrumentation. And on the left, you can see some clear colors like red, some blues, and some green. And in this range, that really tells us a lot about those galaxies, whether they have a lot of dust, whether they don't have a lot of dust, whether they have organic molecules in them. So the red ones are dusty galaxies. The blue ones are not very much dust. And these greenish ones here, scientists think that these are regions where there's a lot of organic molecules. The things that make up our bodies are there. So possible level. So this is some more science from this same image. They were able to look at some really, really faint galaxies, right? They're looking back in time at some of the oldest galaxies that exist. And you can see here they're showing the redshifting of particular elements at certain frequencies of their light. And what that means. And so the one on the bottom, 13.1 billion years ago, this is the oldest galaxy that we had there, that we know of from this image. And it's super faint. This is that same region, and just some more of the what we call chemical spectra of them. This is just like a signature. You just sign a check or sign your name or something. That's something that you do that's unique to your identity. The elements, hydrogen, oxygen, nitrogen, all of them have their own unique patterns of light that they like to absorb and also release. And so that creates a chemical signature whenever we look at them with this. You know what the
Well, I've seen those kind of pictures before. Is that you're actually seeing the pixels?
Yeah, this is a false made image, right? Like they take the data and they create a picture.
Oh, I didn't know that.
Pixel by pixel. So this is Hubble's picture of Jupiter. As Jasmine mentioned, I like to use my Dobsonian, which is like that telescope there, that white one, to just look at planets. It's just fun. That's what I like to do with the students that I work with. It usually ignites their interest in astronomy whenever they see something like that they've always seen in books or pictures of. When they see it with their eyes, it's really fun. And so I'm kind of addicted to that. Like, you know, that's why being a teacher was to turn the light bulb on. Well, that's the same exact reason why I'm addicted to doing this with people. So this is the visual image from Hubble. You can see the red spot, and that I believe is the moon Europa. This is from the Webb Space Telescope in July of last summer. Where'd the red spot go?
That's the red one.
Yeah, it's white now. Any idea why that is?
Temperature. False
Not really temperature. What someone else did? Okay, and it's very apparent in the infrared, right? It becomes brighter. Wonder why that is. It's about the same color of ice, right? Or water. This is likely a very, very high altitude cloud from a solar system on Jupiter. So we're seeing the reflection of infrared off of a material like this. And that's also why Jupiter's rings become visible in this image. There's a couple other moons of Jupiter in here as well. You can see the auroras and some of the diffraction of the light from the auroras. How many of you knew that Jupiter had rings until before today? Yeah. When I saw this, I was surprised. Anybody know what planet this is? What do you think? Everyone say your guess. What do you think? Pluto? Neptune? Uranus? It's Neptune. It sounds like the majority of you got that right. This is over 16 days, and so it's one complete rotation of Neptune. And this was with Hubble. Let's take a look at it with Webb. So that the planet got really dim, didn't it, compared to what it looked like, a really brilliant blue color. That's methane. Methane is CH4, so it's all of those CH bonds that I talked about back on the first slide. They absorb infrared energy very well, so that's why the planet looks dim. But there are also latitudes where there's a lot of clouds that are formed. Just kind of like on Earth, where there are places where air rises, it creates places where there's a lot of storms. That's what's happening in some of these places that are bright. And if you come up to my computer and take a look right around the equator, it's a little bit brighter than it is everywhere else. And that's because it's a little bit hotter and things can expand a little bit better and create that effect as well. You can see the rings appear here. You couldn't see that in the visual spectrum either. And Triton, which is a moon of Neptune, actually appears brighter in infrared than the planet does, which is kind of neat. And so after they did that, they were like, okay, well, we're going to take some pictures of Uranus then, because this is, I think they were surprised at how well the telescope is actually working. job of making very thin green-like structures appear that you can't see in the visible spectrum. So Uranus, this is Uranus here. You kind of see the main ring here in the with the Hubble. Kind of think on the projector screen. There it is with the Webb Space Telescope. You can also see the auroras. What do you notice? Where's the aurora taking place?
In like a yellowish or reddish spot.
It's here, right? Normally we see auroras like here, right? So Uranus is actually flopped down on its side. This is one of its polar regions. So about 2 weeks ago, they announced the 4 astronauts that are going to be part of the Artemis 2 mission. I can't remember their names. 1 is female, 3 are from the United States, and 1 is Canadian. And they're going to make an orbit around a manned mission, and they're going to come back. And so they're also going to set up some things to prepare to install Gateway, which is going to be an orbiter that goes around the moon that you can dock to, and once you dock there, then you go to land the moon, and you can also launch back and reconnect. Come back to Earth, or go further up the line maybe in the future, something like that. Big as the International Space Station, but it has room for cargo, the crew to be whenever they're there for temporary, exchange between the moon and other places. Not a very long time at all. So yeah, the first mission was a success, and it was a huge delay also from a launch pad. There were some fuel lines and things that they couldn't figure out why they were leaking. They took the time with it, and it worked. It was a success. So that's got to be super reassuring to those astronauts. Go out on the next run. You have a question?
Yes, like in the future, they send a man to Mars, the man has to go to Mars, have to build a suit to see what it is being like on another place than Earth.
Well, and we need just like Joe said earlier about getting interested in astronomy, you just have to start somewhere, and you don't have to do all things. Just find somewhere to start, and then keep working and leaping from there. So why not go to the moon, which is our closest neighbor, as our starting spot?
Yeah, someone's already been there, so you know you can do it.
We know we can get there. All right, well, thank you.
Thank you, Josh, for that presentation. Does anyone have any final questions about any presentation?
All right.